Hey, um, today I will talk about problems that require you to find the quotient and the remainder. Okay, so uh, the division operator, okay, and the modulo operator. Okay, so this would give you the quotient of a division, right, and this would give you the remainder of a division, right. To recap, what is the quotient and what is the remainder? So let's say you're dividing uh, 10, right? You're dividing 10 by 3. The result would be something like 3 decimal, 3 decimal, or if you want to express this in mixed fraction, it would be 3 and then 1 over 3, right? So this 3, the integer part is the quotient, right? And the numerator in the fractional part is the remainder. Okay, so what are the problems that require you to find the quotient and remainder? Here are a few examples. Okay, so as we have seen before, if you want to split if you want to split a number into individual digits, okay, without converting it into a string, okay, if you want to do that, then you would have to use these two operators, okay, integer division and modulo, or you have to find the quotient and the remainder, right? Another example is divisibility. If you want to examine if a number is even or odd, or you might want to examine if a number is prime or not, right? So such problems that deal with divisibility are also um, use cases of these two operators. Okay. Um, the other set of examples is these two, right? So one is like converting elapsed time in seconds, right? From seconds to hours, minutes, and seconds, or convert some amount of money to $100 bills and $50 bills and $20 bills and so on, right? Um, the other type is calculating greatest common divisor or least common multiple, least common multiple. Okay. Again, this determining if a number is a palindrome without converting it into a string. Again, this is sort of related to splitting a number. Okay, this is related to the splitting a number. As long as you have the individual digits, you can do whatever you like with it, right? Count the number of digits within a number. Again, with very similar to this one, like related. Once you get the individual digits of a number, you can do tons of stuff, right? Same as this. Okay, once you get the digits, you can sort of answer this question, that how many times a specific digit occurs within a number. Okay, and all of these without converted into a string. Okay, you might think, okay, why not, right? Why not convert it to a string? There are two reasons for it. Firstly, the first reason is string conversion is expensive. It's expensive. Okay, which means if you are to perform this operation, right? For example, if you want to perform uh, this operation right here, okay, split the number, or maybe um this one, check if a number is palindrome or not, right? If you want to do this on one number, right, one integer, it the computer would do it very quickly, right? It's very fast, right? But if you do it on 1 million, on 1 million integers, right, uh, it would make a difference. Okay, if you convert it into a string, or maybe 10 million or maybe 100 million, right? If you convert it into a string, you will see a difference in time. Okay. uh, the other point is the string conversion. It's in Python, it's easy, but since we are learning programming and not Python per se, okay, in general programming, it's not always straightforward to convert a number to a string. Okay, so but that's a minor reason, but the major reason is it's more expensive. Okay, and it's like it's more natural, it's more natural to use the quotient and remainder if your input is a number. Okay. Now, one quick point before we go ahead. Uh, in your final exams, you can expect at least one question or one problem that requires you to calculate the quotient and the remainder. Okay. It may be between amongst these types of questions, right? I'll try to keep it amongst these types, right? But you can at least expect one question in which you are required to find the quotient of the remainder. Okay, so let's start talking about the quotient and remainder. Okay, so this program is quite simple. It asks you to enter a number, enter two numbers actually, and then it finds the quotient and remainder. Okay, so let's say you enter two numbers, 5 and 10, right? Now the integer division, okay, is essentially you divide one number by the other and take the integer part. You sort of ignore the decimal part, right? So when you divide 5 by 10, right, what would be the answer? The answer would be 0.5, right? Now, what is the part before decimal? It's 0. Okay, so the q would be 0, the quotient would be 0. Okay, now the modulo gives you the remainder of that division. Okay, now if the first number or the numerator is smaller, right, it will obviously give the return the numerator, right? So essentially when you say 5 over 10, it's like saying, it's if you wanted to convert into a fraction, this is a fraction. If you want to express this fraction in a sort of a canonical form, you would say 0 and then 5 over 10, right? So 0 is the whole part. It's a mixed fraction, right? 0 is the whole part, which is the quotient, and 5 is the remainder, right? That's 5, right? If the first number is if the numerator of the division, so let's take any number, right, x over y. If the numerator is larger, if x is greater than y, right, then the quotient must be greater than 1, right? And if x is smaller than y, then the quotient, actually this is greater than 0. The quotient, this would be greater than 0, and this would be the quotient would be uh, equal to 0. Okay, so in this case, actually if x is greater than or equal to y, okay, so in this case the numerator is smaller than the denominator, right? That's why the quotient is 0. Okay, so this is smaller than this, that's why the quotient is 0. If we reverse it, right, if we say 5 over 10, I'm sorry, 10 over 5, okay, so if we say the first number is 10 and the second number is 5, okay, this is 10, okay, the second number is 5, then q would be 10 over 5, which is 2, because the division is 2 decimal 0, so I'll take the 2 part. The remainder would be 0, okay, because 10 is perfectly divisible by 5. So if this is 10 over 5, q will give me 2, that's the quotient. The remainder would be 0, right? So this is especially useful if you have something like maybe a situation where it's not perfectly divisible, maybe, right? So for instance, let's say 13 over 3. Okay, so what is this? This is 4 decimal something, right? So if you convert this into a mixed fraction, 13 over 3, what will this give you? Okay, this will give you this is 12 plus 1 over 3, that is equal to 4 and a third, right? So this is the 4 is your quotient, right? And the 1 is the remainder. right? So that's how we use these two uh, these two operators right here to get the quotient and the remainder, right? So this will give you the quotient, right? And this will give you the remainder. Okay. Now there is another way of doing this, and that is using the built-in div mod method. Okay, division modulo. Okay, and what happens is the div mod is a function that returns two values. Okay, it's a subroutine. No, it's a function actually. It's a function that returns two values, right? So div mod will take two numbers. Okay, this function will take two numbers, and it will return two values. The first value will store the quotient, and the second value will store the remainder. So if you don't want to use these two lines, you are free to use the divmod built-in function in Python. Okay. Okay, so let's start with the first use case of quotients and remainders, which is testing divisibility, right? So we know that we say that a number x is is divisible by y, by any number y, if the remainder is 0, right? If the remainder is 0. Okay, so example, 10 and 5. 10 is perfectly divisible by 5 because you divide 10 by 5, you'll get 2 decimal zeros. So there is no remainder, right? No remainder. Again, 4 over 4 over 1, let's say 4 over 1, that's also 4 decimal 0, right? So no remainder. Okay, but let's say you have 5 over 2, that will give you 2 decimal 5, right? There is a remainder, so it's not divisible. 5 is not divisible by 2, right? So one of the most important applications of testing divisibility is finding out if a number is even or odd. Okay. Now, when is a number even? A number is even if it's divisible by 2, right? So a number is even if it's divisible by 2. And it's odd if it's not, right? So examples of even numbers: 0, 2, 4, 6, 8, so on. Example of odd numbers: 1, 3, 5, 7, and so on, right? So how would we find out if a number is divisible by 2? Simple. We use the modulo operator. Okay, we do not use the integer division because we don't care about the result. We don't care about the quotient, right? The quotient is irrelevant, right? Quotient is irrelevant. We do not care about the quotient. All we care about is the remainder right here. And what gives us the remainder? This modulo, right? This modulo operator. Okay. Okay. And this will give us the remainder when that number is divided by 2, right? So the first thing we do is we ask the user for an integer, right? The user gives me a number, let's say 37, right? So I check if 37 is divisible by 2 or not. So 37 modulo 2, is it equal to 0 or not, right? Now in this case it's not. So this if statement, this will evaluate to false, right? This right here will evaluate to false. Okay, this will be false, and we will come to the else block. So this statement, this function will print n, which is 37. 37 is odd. Okay, if you were to give 36 instead, if you were to give 36 as input, then this would evaluate to true, right? This will evaluate to true, and then it will print n, which is 36. 36 is even. Okay, so that's one of the most useful applications of quotient and remainder, testing divisibility. Okay, another example, here we just trying to find out if a number is divisible by 5 or not. Okay, so it's the exact same as before, except here we check for n modulo 5, right? N modulo 5, and that gives us, if this is 0, this means the number is divisible by 5. This is, if this is true, then the number is divisible by 5, right? Now what this boils down to is things like finding if a number is prime or not. Okay, so when is a number prime? So let's take a number, let's take 7 for instance. Let's take 7, right? Now a number is prime if it's only divisible by 1 or itself, right? So it's not, 7 is obviously divisible by 1, right? It's divisible by 1. It's not divisible by 2. You cannot divide 7 by 2 because it's 3.5. You cannot divide it by 3. You cannot divide it by 4, 5, 6. You can divide it by 7, obviously, because 7 divided by 7 is 1, right? And 1 divided by 1, 7 is, sorry, 7 divided by 1 is 7. So a number is prime if it is not divisible by any number between 1 and itself. Okay, and that's our hint, right? So we want to find out if a number is prime or not. So if you take a non-prime number such as, let's say 8, right? If you want to say 8, now 8 is obviously divisible by 1. It is divisible by 2. It's not divisible by 3, but it is by 4, not 5, right? Not 6, not 7, and then 8 again. Okay, so because it is divisible by, apart from 1 and 8, it is divisible by 2 and 4. 8 is not a prime number, right? So in this example, it's a rather simple example, but what we want to find is if a number is not prime. Okay, if you want to find if a number is prime or not, it's a very small change. But in this case, we are trying to find out if a number is not prime. Okay, so what we do is we ask the user for a number. Okay, let's say the user enters 7. Okay, and then what we do is, remember that a number is prime if it is not divisible by any number between 1 and itself, right? So it'll all obviously be divisible by 1. So we want to check if it's divisible by, if 7 is divisible by 2, 3, 4, 5, 6. Okay, and what is this? This is essentially range. This is a range starting from 2 and ending at, but not including 7, right? And that's what's happening here, right? This is 2, this n is 7 because that's what I entered, right? So for every value in the range of 2 through 6, okay, or 2 through 7, not including 7, okay, we check if the number that I entered, 7, okay, that 7 is divisible by that number in the range or not. Okay, if it is divisible, I can say for sure that is definitely not prime. Okay, I don't need to move ahead, so I break out of that loop, right? Because if let's take the example of 8. Okay, let's take the example of 8 instead. So 8 is obviously divisible by 1. Okay, it's divisible by 2 as well. It's not divisible by 3. It's divisible by 4, 5, 6, 7, and then again 8. Okay, so obviously we're not going to check 1, right? We're not going to check 8. So we are going to check for every number in this range 2 through 7, right? So initially I equals 2. Let's say I, this is I, okay? This is my I equals 2, okay? And n equals 8, okay? So if 8 is divisible by 2, which it is, right? Which it is. So in here, in this case, in this example, let's assume that instead of 7, I entered 8. The user entered 8. Now this n would be 8, right? This would be 2 comma 8, which is 2, 3, 4, 5, 6, 7, right? Now if n is divisible by I, so initially I equals 2, is 8 divisible by 2? Yes, it is. This statement is true, right? If this statement is true, I can say n is not prime, which is to say 8 is not prime, and then I break out of the loop. Because if it is divisible by any one, at that point it ceases to be a prime number. I do not need to go ahead and check every other number in the list. It does not make any sense, right? You can, but it doesn't make any sense. You just break out of that loop, right? You come here and then you continue, okay? If on the other hand, the number is indeed a prime, okay? For example, if the number is 7, okay? For I in range 2 through 7, okay, 2 through 7, which is 2, 3, 4, 5, and 6. So for every I, right, initially I would be 2, that's my I would be 2, okay. I check if n modulo I is equal to 0, which means I want to check if n, the number n, which is 7, that's 7, right? If 7 is divisible by I or not, and what is I? I is 2. So 7 is not in fact divisible by 2, okay. 7 when divided by 2 leaves a remainder of 1, right? So this will evaluate to false, okay, and nothing will happen. This block of statement will not be executed, right? This will not be executed, and I will go back to my loop, right? And then I would be incremented. So now I would be 3, right? I would be 3. So I keep the thing, I do this, execute this block of statements again, except instead of I equals 2, I check for I equals 3, right? So this would be, is 7 modulo 3 equals 1 or not, right? And I'm not equals 0 or not. That's the question I want to ask, right? Is equal to 0 or not? That's the question that I want to ask. And again, 7 divided by 3 would leave me a remainder of 1, okay, because 3 times 2 equals 6. 3 2s are 6, and then there's 1 remaining, right? So it's like a mixed fraction, right? So it's 7 over 3 equals 2 1 over 3, right? That's a mixed fraction. So there is a remainder. So this will again evaluate to false. Same thing, I will go up, I would be incremented. So now I would be 4, right? I would be 4, and the set of statements would be executed again. 7 modulo 4 would be 3 actually. This time 7 modulo 4 would be 3, okay? Because if you try to divide 7 by 4, you get a remainder of 3. 7 divided by 4 equals 1 over 3 by 4. That's the mixed fraction, right? So the remainder is 3. So again, this will evaluate to false. We go back and we keep doing that. Okay, until we are out of the numbers of this range, okay, and out of this for loop. And obviously we stop the program right there, okay. So if the number is not a prime, we say it is not a prime. If the number is a prime, we do not say anything, okay, we just come out of the loop. Now if you want to also say if a number is prime or not, right? So not just this, find if a number is not prime. If you want to say find if a number is prime or not, right? So you say both. You do both, right? You say if a number is prime or if it's not a prime. How would you, what would you do? How would you change this? The only thing that you need to do is you need a temporary variable, right? You need some sort of variable here, a Boolean variable. So the Boolean variable might be called is prime or something, right? You know what? Let me do this. Let me actually code it for you. So it will look like this, right? It will look like n equals int, int input enter a number or something, enter a number, okay? So that will give me my number. And what I want to do is I want to create a temporary variable, okay, which would be updated inside the loop, and the final result would be stored in that variable once the loop is over, okay? So let's say the temporary variable is called is prime, which is initially set to true. So by default, we assume that the number is prime. Okay, uh, and what we do is for I in range 2 through n, okay, we check, right? So if n modulo I is equal to 0, then obviously is prime is false, right? Because it's perfectly divisible. So is prime is false. We don't need to check any further. I'm sorry, we don't need to check any further. So we break out of the loop, right? We break out of the loop, and that's that, right? If on the other hand, the number is if the number is no, at this point we break up the loop. That's fine. That's enough. Okay, that's what we do. Now, when we want to write the output, all we need to do is we need to check the value of this, right? That would be our value. So we can just say uh, uh, if is prime, right? If is prime is true, then we would say print n is prime, else else we would say n is not prime, and that's it, right? Okay, it says expression can be simplified, so you can say is prime. If is prime, you can say this as well. Okay, so when you run this, let's say you say 36, let's say 36 is not prime. If you say 37 is prime. Okay, so the next type is what we have seen before, splitting a number into individual digits. Okay, and as you might already see, it's a bit messy, right? It's a bit messy. But if you use the Divmod, uh, with a small d, I'm sorry, Divmod uh, function, it becomes much easier. It becomes like this. Okay, now what's happening here? What's happening here is we are given a 6-digit number, and we are iteratively dividing it, okay, by smaller and smaller values, right? We are making it smaller and smaller and extracting each of the digits starting from the leftmost digit. Okay, how? So what's happening here is, again, I'm not going to explain this, because if you understand the Divmod one, this would be simple for you as well. But I'm going to do this, right? So Divmod will give you the quotient and the remainder, right? So let's take a 6-digit number. Let's take the number 1, 2, 3, 4, 5, 6. That's my 6-digit number. Okay. So when you divide this 6-digit number, right? When you divide this 6-digit number, you know what? Let me make it smaller. Let me do this. When you divide this number 1, 2, 3, 4, 5, 6 by 1, 0, 0, 0, 0, 0, right? If you express this as a mixed fraction, what will the result be? The result would be 1 over 2, 3, 4, 5, 6. I'm sorry, 1 and 2, 3, 4, 5, 6 over 100,000, right? So essentially, if you take the quotient and the remainder, right? If you use the div mod of the number and 100,000, okay, this will give you 1 as the quotient and 2, 3, 4, 5, 6 as the remainder, right? So what happened was, you have extracted the leftmost digit. The leftmost digit has been extracted from this number, right? Now what we do is, this is the remainder, right? The R is the remainder. What we do is, instead of actually using the number, we start using the remainder from now on. Okay, so the remainder was then divided by 10,000, right? So what was the remainder? 2, 3, 4, 5, 6, right? And by the way, the quotient was stored in this variable called digit1, because we have sort of extracted the leftmost digit, right? Um, you know what? Let's do this. Let's, instead of 1 2 3 4 5 6, let's take a random number rather. Let's take 6 7 6 7 2 3 5 4. That's my number. Okay, so when you divide this number by okay 100,000, right? If you express this as a mixed fraction, what you get is 6, right? That's your 6 decimal something, 6 decimal 7 2 3 5 4. That is your quotient, and that is your remainder, right? Right. Uh, so essentially, if you express this as a mixed fraction, what you get is 6 over, I'm sorry, 6 and 7 2 3 5 4 over 100,000, right? So this would be my quotient, this would be my remainder, right? Now this quotient would be saved as digit 1. So digit 1 would be 6. And the remainder, what is the remainder? The remainder would be this, right? 7 2 3 5 4. 7 2 3 5 4. So what we have done is, with this div mod, right, using this original number and the div mod, we have extracted the leftmost digit, which is 6, stored it in digit 1, the variable digit 1. We have taken the rest and stored it in the variable r, right? So r contains 7 2 3 5 4. So we have extracted the leftmost digit, right? Now next, the leftmost digit is then divided by 10,000. So the leftmost digit was, you know what, the number was 6 7 2 3 5 4. So the leftmost digit, digit 1 was 6, the remainder was 7 2 3 5 4. So this division right here, this would be div mod 7 2 3 5 4 and 10,000. So the first one was 100,000, right? So this is 6 digits, this is 5 digits, right? And the next one would be 4 digits, 3 digits, 2 digits, and so on, right? So again, if you express this as a mixed fraction, this will give you 7 and 2 3 5 4 over 10,000. Okay, now the 7 would be stored as the q, as the quotient, which is digit 2, right? This 7, and the remainder would be stored in r. Okay, so what is r? R is 2 3 5 4, right? Now this 2 3 5 4 is then divided by 1000. So now what we do is 2 3 5 4 by 1000. Again, expressed as a mixed fraction, it looks like 2 and 354 over 1000, right? So 2 is our digit 3, and the remainder would be 354. That's my remainder, right? 354. I'm sorry. Yeah, that's 354. Now this remainder goes here, so we div mod 354 by 100, right? So 354 over 100, when expressed as a mixed fraction, would be 3 and 54 over 100. So that's my 3, and this is 54. This is 54, right? Now this 54 comes here, that's 54. So what we do is 54 div mod 10. So 54 over 10, it can be expressed as a mixed fraction, which is 5 and 4 over 10, right? So 5 is my digit here, right? 5 is this digit, and the remainder is 4. Now what we do is we save 4 as digit 6, obviously. Okay, so what you could do is, instead of digit 5r, you could have said digit 5 comma digit 6. Okay, so instead of this, you could have said digit 5 comma digit 6 equals div mod r 10. Okay. Now, if you go through this example, if you go through this code right here, it's doing the exact same thing. The only difference is, instead of using divmod, it's using these two operators, okay, the integer division and the remainder, okay, but essentially it's doing the same thing. It looks a bit messy, so I would prefer the divmod, okay, I would prefer the divmod function, okay, because I would assume that if you can use the divmod function properly, I would assume that you know what's happening here, okay, what's happening here as well, okay. So that's how you get the individual digits in a 6-digit number, okay, without converting it into a string, okay. Now there is another way of splitting the numbers, and that involves splitting the number from extracting the digits from the right, okay. So previously what we did was we had a 6-digit number such as 6 7 right 2 3 5 4, I think, and what we did was we extracted the number 6 and got the remainder, right, 7 2 3 5 4. From here we extracted 7 and then worked on 2 3 5 4, and then we got 2, right, and then got 3 5 4. From there we got 3 3 and 54, and then we got 5 and 4, right. So we started extracting from the left, right, but there is another way of doing it from the right, okay. So given a number, again 6 7 2 3 5 4, okay, we can extract the numbers from the right as well, okay. And the way we do it is we divide this by 10, and again take the quotient and the remainder, but instead of saving like here, instead of saving the quotient, right, and working on the remainder, here we save the remainder, right, and work on the quotient. How? So let's take this number 6 7 2 3 5 4, okay. So 6 7 2 3 5 4 when divided by 10 will give you a sort of an improper fraction, right, which is, what will the fraction be? It would be 6 7 2 3 5 and 4 over 10, right. That would be the answer, right. So this would be your quotient, this would be your quotient, and this would be your remainder, right. So what we have done here is, instead of splitting this number 6 7 2 3 5 4 6 7 2 3 5 4, instead of splitting this number like this, okay, we have split this number like this, okay. This was my first approach, which is this approach right here, right, and this is this approach, okay. So instead of splitting it like this, we have split it like this, okay. So we take the quotient, which is 6 7 2 3 5, and extract the last digit, which is 4, okay. So the last digit is d6. I chose to save it in a variable called d6, okay. So at the end of this statement right here, q would contain 7, I'm sorry, q would contain 6 7 6 7 2 3 5, and d6 would be 4. Now this 6 7 2 3 5 stored in q would be then used in the next statement, and we again divide it by 10, okay, we again divmod it by 10, and what happens then? Essentially this is 6 7 2 3 5 divmod 10, which is 6 7 2 3 and then 5 over 10. So 6 7 2 3 is the quotient, 5 is the remainder, right. So the quotient would be 6 7 2 3, right, and the remainder would be 5, and that 5, the remainder, is stored in the variable called d5, okay. And this quotient is then sent to the next statement right here. So again 6 7 2 3 over 10, right, So 6723 over 10, which will give you 672 and then 3 over 10, right? 3 over 10. So 672 is the quotient, 672 right here, and D4 is 3. D4 is 3. Now the quotient again goes to this statement right here. Same thing as before. Instead of 6723, we do 672, right? I'm sorry, instead, yeah, 672 over 10, which will give you 62 and then 2 over 10. So this would be 62 and this would be 2, right? The 62 is sent here, so this would be 62. 62 over 10, I'm sorry, 67, I'm sorry, 67. This would be 67, okay? 67 over 10, which will give you 6 and then 7 over 10. So this is 6, this is 7, okay? And that's what we do here, okay? So instead of extracting the numbers from the left, this will let you extract the numbers from the right. Now look at this. Again, like before, we could have said D2, I'm sorry, Q, or we could say D1 comma D2 equals this and get rid of this statement, okay? It's the same thing. So look at the difference between this and this, right? Now here we start with this number, right? 6-digit number, and then we reduce the number to 5, right? To a 5-digit number, and then 100,000, 10,000, 1,000, 100, right? So we reduce the number of digits in our denominator. But here it stays the same, right? It's 10. It's always 10. Okay. But the difference is here it's in order, right? So it's first digit 1, then we get digit 2 and 3 and 4 and 5 and 6. But here the digits are in reverse order, right? So we get D6 first, and then D5 and 4, 3, 2, and finally we get D1, right? So you can go whichever way you want, okay? But I feel like this would be better if you don't know the number of digits beforehand, okay? So in this case, I say enter a 6-digit integer. So I'm forcing you to enter a 6-digit integer, right? But if you don't know the number of digits, see the amount of duplication in this code, right? So you have the Divmod, right? You have Q, you have the number 10 right here, right? That's the number 10. You have this right here. So there is an enormous amount of code duplication, right? So what you can do is you can use a loop. Don't get me wrong, I mean, you can use a loop here as well, okay? Here is also, there's a huge amount of duplication, and this is pretty simple. It's just, divided by 10. So you can do that as well, but I think this is more amenable to using loops. But anyways, so the reason I mentioned loops is we will need that in the next problem, which says we want to split an arbitrary number, okay? Any arbitrary number. So we don't know what the number of digits are, okay? So the number can have any number of digits. What if we have that? I mean, what do we do if we have a number for which we do not know the number of digits? What we do is we create a list. We create a list, an empty list called digits, okay? As usual, we ask the user for a number, for an integer. Maybe the user enters I don't know, a big number, okay, like 8, 7, 4, 3, right, 1, 2, 5, 6, 9, 0, a big number, okay? That's what the user chooses to enter. Now I create initially an empty list, right, using this syntax right here, remember? Now what we do is I run this loop, okay? So I say for n is greater than 10, okay, n/d equals divmod n and 10, which is to say get the number, divide it by 10, and give me the quotient and the remainder, and store the quotient into the number itself, okay? So we have this number n, which is this number right here. The first statement checks if the number is 10 or not. If the number is not greater than 10, right, if the number is less than 10, actually should be greater than equal to. If the number is less than 10, we just append that number to the list and then display the number. Okay, so if the number is 1, okay, or 1 through 9, I just append that to the list. So the list would contain 9, let's say, and then we display the list in the reverse order. Okay, that's reverse, right? So because in this case the list contains just a single element, I'll just display that element, which is 9. Okay, so it takes care of the case where the number has a single digit. Okay, that's being taken care of. Now what next? Let's say the number has these many digits. Okay, a huge number of digits. We start with the statement. Okay, n comma d equals divmod n 10, which means divide this number, whatever the number is, I don't know. All I know is the number is greater than 10. Divide that number by 10. So I'd say 8, 7, 4, 3, 1, 2, 5, 6, 9, 0. Huge number, right? Divide this number by 10. Okay? And give me two things. Give me the result, the quotient, and the remainder. What is the quotient? The quotient is 8, 7, 4, 3, 1, 2, 5, 6, 9. And the remainder is 0. Okay? Now the quotient is stored, the quotient replaces the original number, right? So this is n, this is n right here, and this was the old n. So now the new n has the value of the quotient. The old n has been replaced, and d gives us the remainder, which is 0, and that remainder is appended to that list, right? The remainder is appended to that list. So the list initially was empty, right? Now it contains 0. Okay, now it contains 0. Okay, so then we go back to this loop. We check, is n greater than equal to 10? Yes, it is. It is in fact greater than 10, right? Because it is 8, 7, 4, 3, 1, 2, 5, 6, 9. So it is greater than 10. So again, what we do is n comma d equals div mod n 10. So this time n is 874312569 So I'm sorry, 9. There's no 0 anymore. So when you do this, when you calculate this, it will give you the quotient, which is 874312556, not the 9 anymore, and the remainder would be 9. The remainder would be 9. Now this is stored here, right? N gets this value right here. This value is stored in n. So the old value is replaced by this new value, and the d, that's the remainder, that's saved here, and eventually it is appended to the list. Okay, so this time, the second time the loop runs, what we will do is the list will contain 0 and 9. Okay, now again we run the loop again, we check this, right? We check if n is greater than equal to 10, and yes, it is greater than equal to 10, right? It is greater than 10 because n is this number right here. N is 87874312556, which is greater than 10, right? So we again do this thing, we calculate div mod of n 10, right? And n is this number right here, and the result would be this number and 6. This number would be stored in n, that's the new value of n, and d would be 6. Now that d would be appended to that list, so our list will contain 6. Okay, again we check for n, right? If n is greater than 10, yes, it is greater than 10. We do the div mod, we do the deed, right? So this is this, right? And 5, this is stored here, right? The old value of n is replaced by this number right here, okay, this number, and 5 is appended to that list. Okay, so the list now has 5. Okay, and this goes on and on. Okay, this goes on and on. Okay, so by the time you're done, okay, if the number was the whatever the number was, the big number, right? Again, 6798321054, something like that. Okay, if the number was like that, the digits, the list would contain the digits starting from the rightmost one, right? So it will first have 4. It would be 4, and then 5, and then 0, 1, 2. By the way, this is greater than equal to 10. Okay, 2, and then 3, 8, 9, 7, 6. So if you want to print the digits, all you do is print the digits in reverse. That's how we print the list in reverse, right? And this gives you an idea of how to perform this action on an arbitrary number of digits. Okay, the next example is very similar to the problem that we had in one of the assignments, which is given a currency value, we had to sort of split it into dollar bills, right? This is sort of similar, except the only difference is given the elapsed time in seconds. This elapsed time would be initially in seconds. We have to calculate what is that time in hours, minutes, and seconds. Okay, so what we do is we get that number, right? We ask the user for the number of time, the time in seconds. Sorry about the background noise if you hearing that. So the number would be whatever the number that's entered by the user, right? And what we do is we first divide that number, okay, by this number 86400, which is the number of seconds in a day. Okay, so a day contains 24 hours, each hour contains 60 minutes, each contains 60 seconds. So that's the number of seconds in a day. So if you divide this number, whatever the number was, by this number right here, 86400, it will give you the number of days and the remaining number of seconds. Okay, now that remaining number of seconds would then be divided by 3600. What is 3600? It is 60 times 60, which is the number of seconds in an hour. Okay, if it's not equal to, if there is a remainder, right, it must be less than a day, right? So this is, again, we use the Divmod to find this, and that will give me the number of hours, and the remaining will be minutes. This would be again sent to the Divmod, and we divide it by 60, right? And this will give me the minutes and the seconds. Okay, so we did an example of this before, but this just goes to show that it's not just dollar bills, right? It can be also problems of this type as well. And the idea or the commonality of these types of questions is that every time you start with the largest value, right? So in case of the bills, if I want to calculate, let's say, the change of currency, right? Or let's say, given a currency value, I want to sort of calculate how many $100 bills I have, and how many $50 bills I have, right? How many $20 bills I have, and so on and so forth. We always start with the largest value. Okay, in this case, we start with this, the number of seconds in a day. Okay, the number of seconds in a day is this. If the original number is larger than this number, obviously it's more than 1 day. If it's not, if it's less than 1 day, we go to the next one, it's hours, right? The next thing is, once we get the days, right, we always use the remainder. The original number we don't use anymore. Okay, we always use, this is not used anymore, we use the remainder, excuse me, and the remainder again. Okay, and finally, the last division, the last Divmod calculation would give you two two useful answers, the minutes and seconds. Same as before, right? Same as here. Essentially, this is D1, D2, right? This is D1 and D2. The last div mod will always give you two answers. Okay, same as here, right? This could have been written as instead of digit 6 equals R, I could have said digit 5 and then digit 6. Okay, so the last div mod gives you two answers. Just remember that. Okay. Okay. The next problem is finding the lowest common multiple of two numbers. And what it does is, given two numbers, okay, let's say the numbers are 2 and 5, okay, 2 and 5, although it's a simple one. What is the smallest number that is divisible by both 2 and 5? The number is 10, right? You cannot find a number that is smaller than 10 and divisible by both 2 and 5. Okay. So similarly, let's take the numbers 6 and 10. 6 and 10. Okay. What is the smallest number that is a multiple of 6 and 10? Or what is the smallest number which is divisible by both 6 and 10? And the number is 30. That's the number. Okay. You cannot find a smaller number that is divisible by both 6 and 10. Okay. So this is called lowest common multiple. Okay. I'll just call it LCM from now on. So how do we calculate the LCM of two numbers? So given two numbers, right, we first get the numbers from the user, X and Y. Okay. And what we do is we find the maximum value. Okay. You don't have to do that. You can actually go for 1 as well. So you can say M equals 1. Okay. But I'm just going to do it. I'm just going to start with the maximum value, because we use the observation that if a number has to be divisible, this is the LCM, right? This is the LCM. The lowest common multiple must be at least as large as one of the numbers. Okay. So it cannot be smaller than the largest number. You cannot have two numbers, let's say 5 and 10, right? The lowest common multiple of these two numbers, 5 and 10, is 10, because that is the number that is the smallest number which is divisible by both 5 and 10, right? You cannot have a number, you cannot have things like 8. It's simply not possible, because 8 would not be divisible by 10, right? It would not be divisible by 10. So at the very least, the number would be, the LCM, the result would be as big as the largest number, which is in this case 10, right? It cannot be less than 10. So this is the observation that we use. Okay. But you can also start with 1. You can also say M equals 1 and start from there. Okay. Also, in order to find out the maximum value between these two numbers, we are using this Python built-in function called max. Now the max of two numbers X and Y would give you the greater, right? The greater of X and Y, obviously, right? So what we do is we start with M equals, you know what, let me get rid of this. So let's say the first number is 6, the second number is 10. So M equals max of X and Y, which is 10, right? M equals 10. We start with M equals 10. Now what we do is, while true, which is an infinite loop, okay, we check if the number M, okay, think of this as a guess. We are like guessing what the answer is. We start with the guess 10. Okay. Now if our guess is divisible by the first number, which is 6, and it is also divisible by the second number, which is Y, we just go ahead and say that the lowest common multiple of X and Y is M. So this is our answer. The guess is correct. Guess is correct. Okay. And if it's correct, we break, because at that point we have found the lowest, right? So lowest common multiple, so we just break out of the loop. So end the program there. End the program. We break out of that loop. Okay. If on the other hand, if either one of these conditions is not satisfied, if either one of these conditions evaluate to false, we increment m and start all over again. So now m is, the guess 10 was proved to be the incorrect answer, so m is now 11, and then we go again, we check again, right? We check if 11 is divisible by 6 and 11 is divisible by 10 or not. So in the first case, right, if this were 6 and 10, 6 and 10 and m equals 10, the m modulo x, x is, remember, 6, right? This will evaluate to false. Although m modulo y, where y is 10, will evaluate to true. This would be true. This would be true, but this would be false. This is false, okay? But because we have this and, which means we want both these conditions to be true. Only if both these conditions are true, only then we can say that this is in fact the lowest common multiple of x and y, right? But that is not the case here, because this statement is not. 10 is not divisible by 6. 10 when divided by 6 would give you a remainder, right? Remainder of 4. Okay. So that's how we start. Okay. So we start with the maximum. Okay. By the way, you can also start with 1. You could have said m equals 1. But it doesn't make any sense, obviously. If the numbers are 6 and 10, obviously 1 through 10 cannot be an answer. Okay? It cannot be, right? So that's why. But if you start from m equals 1, it will give you these. It will still give you the correct answer. The correctness of the answer won't be compromised. It's just that it's useless. It's redundant. Okay. So we start from the max, right, which is 10, and check if that number is divisible by both x and y or not. If it's not, if it is, we say it is the lowest common multiple. Else we increment that number and then go all over again. So the number would now be 11. It would be 11 because the guess 10 was incorrect. Check again, doesn't work. 12, guess, check again, doesn't work, right? Keep going, keep going, keep going. 30. Okay, so is m modulo, so is 30 modulo 6 equals 0? Yes, it is. This would be true. Is 30 modulo 10 equals 0? Yes, it is. This will be true as well. At that point, we can say the lowest common multiple of 6 and 10 is 30. Okay, and then we break out of that loop. That's where the program ends. Okay. Finally, the last question wants you to find out the greatest common divisor of two numbers. So what is the greatest common divisor? Greatest common divisor of two numbers is the largest number that can divide both the numbers. Okay, so let's say two numbers 4 and 6. Now the greatest common divisor is 2, because 4 is divisible by 2 and 6 is also divisible by 2. Okay, let's take two other numbers like 5 and 15. The largest number that divides both of these two is 5, because 5 divides 15, right? 5 is divisible by 5, 15 is also divisible by 5, right? Sometimes the answer would be 1. For example, if the numbers are maybe 6 and 7, the number would be 1. The answer would be 1, because 1 is the only number that divides both 6 and 7. Okay, there is no other common number between these two. Okay. Another example, maybe let's try 6 and 15. Okay, what is the largest number that divides 6 and 15? The number is 3, right? 6 divided by 3 is 2, 15 divided by 3 is 5, right? So that's it. You cannot have a larger number. It cannot be 4, it cannot be 5, right? Because 6 divided by 4 is not a proper, 6 is not divisible by 4, right? 6 is not divisible by 4. It would be 1 and a half, right? Uh, Definitely not 5, right? Definitely not 6, okay? So this is what we call the greatest common divisor of two numbers, the largest number that divides the two numbers. So how do we solve this problem? As usual, we start with these two statements. We ask the user for two numbers, okay? Let's say the user enters two numbers. 6 is the first number, 15 is the second number, okay? Now what I do is I guess the answer. I take the guess to be the minimum of these two numbers. Why? Because if I want to find the greatest number that divides these two numbers, it certainly cannot be larger than the smallest number, right? It cannot be 7. That's not possible. It's impossible, right? Because 6 is not divisible by 7. It can be at least, it has to be at most 6, I'm sorry, at most the smaller number, okay? So if you have two numbers like 5 and 15, right, the GCD, the greatest common divisor, is 5. It cannot be 15, it cannot be 10, it cannot be 15, right? Because you have this number right here. So the greatest common divisor is at most equal to the smallest number right here, and that's what we guess. That's our initial answer, that's our guess. In this case, our guess is 6. What we'll do now is, inside this loop, we will double check our guess, and we will modify our guess. And by the end of the time, by the end the loop is done, our guess will have the correct result. Okay, so we are guessing that the answer is 6, which is the smaller of these two numbers. Okay, now what we do is, while m is greater than 0, okay, so keep going, we check if our guess is correct or not. When will our guess be correct? If both these numbers, x and y, which is 6 and 15, are divisible by our guess, which is m, which is 6, right? So at the first iteration, remember x is 6, y is 15, right? So x is 6, change this to 6, y is 15. So at the first iteration, 6 modulo m, m is 6, is equal to 0. Yes, this evaluates to true. But 15 modulo 6 does not equal to 0, so this part evaluates to false. So we decrement m and go back, right? Now, yes, m is greater than 0, m is 5 now, so the guess is now 5. We check, is 6 divisible by 5? No, it isn't. It isn't. This one evaluates to false. Decrement the guess, go back. So the guess is now 4. Check again. Is 6 divisible by 4? No, it isn't. Decrement, go back. The guess is now 3. Check again. Is 6 divisible by 3? Yes, it is. This one is true. Is 15 divisible by 3? Yes, it is. This one is true as well. At that point, we know that we have arrived at the greatest common divisor. This is the largest number that can both divide the numbers 6 and 15. Okay, so at that point we print greatest common divisor of 6 and 15 is 3, and then we break out of the loop, which means we end the program right here. Okay, so these are a few examples of problems that require you to find the quotient and the remainder. I will post a list of practice problems. Go through it and let me know if you have any questions. Okay, that's it. See you in the next lecture. Right? Bye.